You are listening to The Vocal Technologist. Spoken tech for your ears.
Welcome back. You know, if your browser is anything like mine, the bookmarks folder is just, it's collapsing under its own weight. I've got white papers, release notes.
Oh, I know that feeling. It's a deluge. Model context protocol architectures, incremental view maintenance.
Exactly. So today, we're going to try and cut through all of that. We've pulled together some really fascinating findings on how companies are building for, massive scale, privacy, and just long-term relevance in this crazy data world.
That's the plan. We're going to synthesize the most critical updates across data engineering, cloud architecture, and maybe the most important part, the philosophical shifts you need to actually build AI agents that work. We're looking at patterns being used right now.
Okay, let's unpack that. I want to start with engineering resilience. Because for anyone building a high-volume platform, just managing the complexity it's the constant battle. What's standing out to you?
Well, we have to start with Command Query Responsibility Segregation, CQRS. It's getting some serious traction again, especially in these really complex microservice setups.
Right.
The whole idea is this really elegant separation. You split your write operations, the commands, from your read operations, your queries. You put them into independent models, sometimes even completely separate databases.
So you're not hammering the same database with, say, a ton of user transactions and all your complex reporting at the same time.
Yeah.
You just scale them separately.
Precisely. Think about a huge e-commerce site. Your checkout, that's the command, it's mission critical and needs to be blazing fast. But your product catalog, the query, that needs massive read scale, and maybe, eventually consistent data is totally fine. CQRS lets you optimize for both.
But doesn't that just trade one problem for another? You get rid of a database bottleneck, but now you have to guarantee eventual consistency across two systems.
Yeah.
That feels like where it all falls apart.
That is the crucial next step. And that replication challenge is solved using tools like Debezium, which uses change data capture CDC.
ETC stuff, yeah.
Exactly. To stream the real-time changes from the write database over to all your different read-optimized databases. It basically turns your write log into a live event stream. We saw a great demo of this with a Quarkus voting app. It just works.
Okay, so that handles the speed and the scale. But speed is useless if your data is garbage. How do you maintain quality in these super complex streaming pipelines? You can't just stop everything for one bad record.
You've hit on the constant tension, right? Integrity versus latency versus cost. And the patterns we're seeing for quality control really detail those trade-offs. There are about 4 main approaches.
Okay.
So on the side that prioritizes like maximum integrity, you have WAP write, audit, publish, and even a WAP, which adds another audit step.
Whoa.
Yeah, they use staging areas, multiple rigid audits. Basically, they block any bad data from ever getting to consumers. But the trade-off is obvious. Super high integrity, but way higher latency and cost.
Like a data roadblock. Effective, maybe, but not exactly built for real time?
Not at all. So then you move to more streamlined things, like tap, transform, audit, publish. It validates the data in memory, which cuts down on I/O. And then at the far end, there's the signal table pattern, which is all about speed but offers the least safety.
I have to wonder, is the real fight there technical? Or is it just getting teams to agree on what bad data even is before you write it?
Oh, it's absolutely a governance problem. The key is that engineers are choosing the trade-off based on the business context. Is this financial data or is it just, user click data? No pattern can save you if you can't define that.
Let's talk about a practical example of this at a massive scale. Stripe, the payment company. What they're doing with their simulation framework it's just jaw-dropping.
It really is. Stripe built this incredibly rigorous regression testing framework on Apache Spark. And this thing can process over 400 billion rows.
400 billion.
Billion. We're talking 2 to 5 terabytes of historical data, and it simulates everything in just a few hours. This is how they backtest changes to their core billing systems.
Wow. So they can validate a whole new pricing model or a system upgrade against years of actual transaction data. What's the secret sauce in that architecture?
Well, the genius isn't just the sheer volume, it's the logic reuse. Instead of rewriting all their business logic in PySpark for the big batch analysis, they architected their core JVM service logic, the code that runs their live system, as reusable libraries.
So the exact same code runs in production and in the massive Spark simulation.
Unified logic, exactly. What you test in simulation is guaranteed to be what goes live. It just accelerates feedback and kills defects before they ever see the light of day. It's really resilience through standardization.
That idea, standardization, brings us to our next section, moving beyond just the buzzwords and focusing on the data itself.
Right. We have to start translating vague terms like modern data stack or data lakehouse into actual engineering requirements. It's so easy to just build complexity because it looks good on a slide, but you risk delivering zero value.
You have to ask the simple questions first. Who needs the data? What's the SLA? How do you trace it?
Yes, a great filter. Which leads to this idea of building an internal schema.org. It sounds like this huge centralizing nightmare, but the way it's described is actually a clever inversion of responsibility.
How so?
So instead of a central data team trying to clean and stitch together data from the entire organization, which is always a bottleneck, each application becomes responsible for mapping its own outputs.
Mapping them to what?
To shared, agreed-upon concepts. So you create this internal dictionary for what customer ID or product SKU means, and every system, whether it's the CRM or the billing platform, has to map its own version to that shared definition.
So the central team isn't cleaning data anymore. They just pull in data that's already aligned to the dictionary, and they can build a knowledge graph almost instantly.
Yeah.
That's smart. It shifts the work to the people who actually know the data best.
Exactly. And this connects to a broader idea called the Cuboid framework, which is all about keeping your data platform relevant long-term.
The Cuboid framework.
Yeah, it maps analytics needs across 3 dimensions: the consumer type, the inquiry mode, and the decision tier. And by plotting those, you start to see all the gaps, the vacant spots in your capabilities.
And once you see the vacant spots, you know what you need to build next.
Precisely. The big takeaway is that platforms that last are the ones that design for those gaps. They do it by treating their data products like stable semantic interfaces, like APIs between the business needs and whatever tools are hot this year. That interface stability is what protects you from tool churn.
Speaking of fundamental stability, let's get down to the basics. Identifiers. UUIDs are everywhere, but they're awful for database indexing.
Yeah.
We saw a really compelling case for switching to ULID.
Yes, ULID, the universally unique lexicographically sortable identifier. It's designed specifically to solve that random insertion penalty you get with ULDs. A ULID is built with a 48-bit timestamp first, then 80 bits of randomness.
And putting the time component first is the key.
That's the whole magic. It makes the IDs sortable by time, which translates directly to better index locality in a database. New records land right next to the last ones written, no more fragmented indexes. It's a huge win for performance in any kind of time series workload.
Okay, let's zoom out. All this focus on resilience, on semantics, it all feeds directly into building AI pipelines. So what does this mean for the AI space?
There's a really interesting point made about why experienced senior engineers often struggle with AI agents.
This is a huge mindset clash and goes right to the core of system architecture. Senior engineers are trained in a deterministic world, strict types, predictable control flow, a culture where any error is seen as a complete failure.
But AI agents are the exact opposite.
They're fundamentally probabilistic. They thrive on ambiguity and natural language. It's not just a technical change, it's a cultural one. You have to accept that 98% correct is the new 100% and retrain decades of muscle memory.
That is a tough pill to swallow. It is. Success here means you have to replace unit tests with evaluations, treat errors as inputs for the next iteration, and just engineer for resilience, not for perfection. You're fundamentally handing over control.
And as we hand over that control, the data these agents train on gets more and more sensitive. So how do we train models on regulated data without centralizing it all and breaking every privacy law on the books?
The answer is practical federated learning, and it really needs 3 distinct layers. First, you need synchronous orchestration, usually with an algorithm like FedAv, to coordinate everything across all the decentralized data silos.
And FedAvG, for anyone who doesn't know, means you're just aggregating the model updates or the weights, not the actual raw data.
Exactly. The model trains locally on the sensitive data, and only the update gets shared. Layer 2 is secure aggregation. It uses things like masking or encryption to make sure even those model updates stay confidential before they're combined. And then layer 3 is differential privacy, which injects just enough mathematical noise to guarantee that the final model can't be reverse engineered to reveal anything about a single person's data.
And this approach has to be tailored to the specific model, right? It's not one size fits all.
Not at all. A model like XGBoost needs a different approach like histogram sharing than something like TabNet, which uses FedAv with specific regularization.
But once you have these powerful agents, you want them to do things, call external tools.
Yeah.
Which brings up the Model Context Protocol, or MCP. And the giant new attack surface it creates.
Oh, the MCP expands the blast radius dramatically. Suddenly you have to worry about content injection attacks, poison tool responses, feeding the agent bad logic, and cross-system escalation if the agent has too many permissions. Data exfiltration becomes terrifyingly easy.
So you have to treat it like critical infrastructure.
Absolutely. Strict privilege boundaries, sandboxed execution for every tool, and a really carefully vetted registry of what tools the agent can even call. It needs to be as secure as any internal API gateway.
Okay, let's wrap this up by looking at the tooling landscape. We saw some huge growth numbers from Microsoft, which suggest data product consumption is just accelerating everywhere.
The numbers are pretty remarkable. Azure as a whole hit a $93 billion run rate, which is 39% growth. But the data products grew even faster. Microsoft Fabric was up 60%, Cosmos DB up 50%, and SQL Database Hyperscale jumped 75%.
That's a huge signal. The integrated data and analytics services are being adopted even faster than the cloud platform itself.
And they're launching new tools to meet that demand. Things like Horizon DB, their cloud-native Postgres, and open-source Document DB. And critically, they integrated Discan-powered vector search across the entire Fabric ecosystem.
That is a serious vector search upgrade. Now, let's get into my favorite part, the deep technical features that save money. StarOx rolled out incremental view maintenance.
IVM is a true game-changer for materialized views. StarOx now supports it with iceberg-backed views. So traditionally, to update a view, you'd have to do a full refresh. Super expensive. With IVM, when the underlying data changes, the view is updated only in proportion to the actual row-level changes.
So if 100 rows change in a billion-row table, you only pay the compute costs for those 100 rows.
Exactly. It uses deterministic snapshot-based deltas. This will save companies running hundreds of these views millions of dollars in compute costs. It's huge.
And finally, a quick update for DuckDB, everyone's favorite analytical database.
Right. DuckDB v1.4.2 now has full delete and update support for Iceberg v2 tables using standard SQL, so you can finally run those update and delete commands that were missing. It's a foundational step to making DuckDB even more powerful in the data lakehouse stack. Just a quick caveat, though. For now, it's limited to non-partition tables and only positional deletes are supported, but it's a great sign of where things are heading.
So if we pull the lens back one last time, it feels like the whole field is moving away from this brittle, deterministic view of the world toward architectures built for resilience and flexibility.
That's the thread connecting all of it. A shift from rigid correctness to systems engineered to handle ambiguity.
And what's fascinating to me are the two big macro trends this points to. First is the realization that AI is going to run out of static text data. The web scrape is finite. So there has to be a huge shift toward experiential data streams from simulations, robotics, sensors, and second, the rising and often hidden cost of cloud fragility. We're seeing how these complex, opaque dependencies in the big cloud providers cause these cascading failures that cost businesses hundreds of millions. So resilience isn't just a nice technical goal, it's a financial necessity.
And this all leads to a really crucial, non-technical question for you listening. All the data suggests AI adoption failures are rarely technical. You can build the most elegant system, but the real problems are human, psychological, and organizational barriers. Only about 6% of organizations actually succeed at scaling AI. And that success is tied directly to what's being called the Cognition X Culture X Control framework.
Meaning, you have to make the tools easier to trust, create a culture where it's safe to admit errors, and maintain human agency even as you hand control to an agent. You can build the world's greatest architecture, but if your team can't adapt to probabilistic thinking, it's just Amos. It's not going to scale. And that's something to reflect on, where your own organization falls on that spectrum. Thanks so much for joining us on The Vocal Technologist, and we'll catch you next time.
Spoken Tech for your ears.